So this weekend I will be talking about an interesting article of Michael Thorpe in AT&T about the title is Fully Dynamic Mincut. Michael Thorpe, I think he is inspired by the work of David Karger, because David Karger has two algorithms. One of them is the popular contraction algorithm. The other one is based on dynamic trees. And the dynamic trees, you need to understand binary search trees, split trees, and the importance of data structure. And in this article, Michael Thorpe, who is a great, amazing researcher in AT&T and now works on an app to fight against corona. So let's talk about his article in 2003. And so when I say K-edge connectivity algorithm, we mean that an algorithm that maintains if a graph is K-edge connected. And so you know that spanning trees may cross a mincut many times. And the most important concept is the concept of a relative load. It means that the relative load of an edge subject to a tree is the number of trees having that edge divided by total number of trees in your tree packing. So this is number of trees having E divided by total number of trees. And the total relative load, as you might guess, is just the sum over all relative loads. And E is a set of edges. And the value, this is really important, the value of packing, because we want to relate packing as a dual of the mincut. And so the value of packing is, we call it pack value of your packing, is 1 over maximum of your relative load over all edges of your graph, of your, I will say when you partition that, then all the elements in in any of the cluster is just contracted to one, though we are talking about the cuts rather than all of the edges. So for T disjoint trees, the pack value is T. You can see why the pack value is T when you have T disjoint trees. But the goal of this article is to construct a tree crossing some mincut only once. And so the first observation that you may notice is that if C is a mincut, and tau is a tree packing. This is a tree packing with a packing value greater than lambda over 2. So it's a definition of average tree. We say it's an average tree because the pack value of tau is greater than lambda over 2. But tau is your packing. It has several it has several trees in it. And so tau contains, the observation is that it contains a tree crossing some mincut. So if this is the mincut, for example, mincut is 2, then there is a tree that contains this. David Karger talks about, for example, says the tree, the cut respects that tree, and the tree 2 constraints. I will talk about it later. But in the work of Michael Thorpe, he proves these important things, that So the observation is that tau contains a tree for some mincut at most once. So it is very intuitive because it's a spanning tree, so it should be connected to all of the vertices somehow. So at least once it should cross the edges, cross the cluster. And the proof is very simple and very elegant, because we just use the properties of maximum. What is maximum in mathematics? And the proof says that, so we have a mincut C, and so the number of edges from C used by an average tree is L2 LTE of C. So LT of E of C, I mean the value, the total relative load of those edges, these edges, the total relative load of them is just the sum over all edges. Is just the sum over all edges. But remember that, for example, tau here is just the average tree. We assume that it's not any tree, it's an average tree. So this is less than E of C maximum. And this is the important things, because each of them is less than the maximum. And by definition, we can say that this is equal to number of the cardinality of this. This is the meaning of pack value that I said. So this is less than lambda over 2, and this is 2. So 2 factor. So consequently, some t in your packing crosses C. So crosses C is strictly less than twice. And since the number of crossings is a positive integer for a given tree, so that means that T crosses C at most once. So for an average tree, L2 of E of C is 2, so there exists a tree that L2 of E of C is 1. It's very intuitive. So let's talk about the duality that I told you. To understand tree packing, we use the concept of dual partitions. A dual concept which is called a partition. So a part value, partition value of your partition is just the number of, it's like K-cut. Number of edges in this contracted graph, and divided by number of clusters minus 1. So, for example, if your partition has only 2 sets, we say P is a cut and a partition value. This is the size of a cut. So let's say that any spanning tree we know that any spanning tree like this, any spanning tree has at least P minus 1 edges. For example, consider this. So we have at least P minus 1 edges. And from E of G P. So we can say that the pack value of your packing is by definition maximum of L2E for all edges. And I said that I use just the properties of the maximum in mathematics. So it's just less than LT of E. E is an E of G P. And of course, here is the cardinality of that set. And this is less than, because this part is less than E of G P times maximum of L2 of E for any E. So we can write this as, this is less than E of G P over P minus 1. And this is exactly the definition of part value. So what we have just proved is that the duality. For example, if we call this phi the maximum of your pack value, so it has become as minimum over partition value of P. So these dualities like mincut, max flow, and all of these things happens in mathematics. And this is another important approach to the problems like mincut or in general k-cut, because we relate our problem, which is just the minimum of your cut partition value, to the maximum of packing value. So if the packing value is higher, we get closer to the optimum, which is minimum of partition value. So we should reduce the minimum of partition value and maximum of pack value in order to reduce this gap, which is, if we reduce it, then it's the optimal. And a tree packing is a greedy if HTI is a minimal spanning tree, with respect to T1, Ti minus 1. Michael Thorpe, when he says minimum spanning tree, many minimum spanning tree, it means that first you pick your minimum spanning tree as usual. Then the next minimum spanning tree, you should find it such that it has the least, let's say, intersection with the previous edges that you have used. And so far until you find all of the trees. So it's not crazy if I say we find many minimum spanning trees. So we should notice what he means. And the Karger you should read the article of Karger's near linear time in mincut that he uses dynamic trees. For example, in his article, he has a lemma that says a greedy tree packing with greater than 3 lambda m over epsilon trees has pack value greater than 1 minus epsilon phi. So the algorithm that we want to talk is very general, because first we pick these HIs because they are random subgraph of G, because Karger uses sampling, because he says that in the big data we cannot just use anything like one by one. We sample it in order to simplify it, because we can create faster algorithm. So HI, it means the random subgraph. You just pick an edge with probability 1 over 2 to the I. So we pick this graph and then construct your greedy tree packing. It doesn't even say how to construct it. It's because it's a general algorithm. So we have log 2 to n trees. So for all the trees in all the tree packings, tau hi, we find the smallest cut in G. So I find the smallest cut in G that crossed at most twice by t. Crossed at most twice by t. For example, this is some spanning tree, but it should cross at most by 2. At most twice by t, and we return finally the overall smallest cut. And so with high probability, we can say that the edge connectivity has this relation with your original edge connectivity. This is the original edge connectivity, but this is a sampled one. Remember, this is the subgraph which is sampled. This is this one. So edge connectivity, so we can relate a simplified, a sparse version of your graph to the edge connectivity of the graph. These are important for just theoretical things. But let's go to see how we can use it for min KV cut. Because mincut is just, we have two sides. But min KV cut is more general. So another article of Michael Thorup, we should read it, that says the title is Minimum KV Cut. KV cuts were deterministic, greedy tree packing. And the algorithm says that it can pack order of MK3 log n spanning trees. So this is the number of spanning trees. And he defined the notion of utilization of an edge, which is the number of times it has been used in previous spanning trees, divided by its capacity. So goal number 1 of this article is to just proving that each minimum KV cut is crossed at most 2k minus 2 times. For example, k minus 1 times, and because for each of them we cross 2 times, so 2 times k minus 1 times, which is 2k minus 2. And the goal 2 of this article is enumerate. This is an important paradigm because rather than just solving an STP or LP relaxation with your Python software, you just enumerate them like 1,000 years ago, 4,000 years ago. You enumerate all such cuts in order of n to the k time. So it is purely combinatorics rather than just combinatorial optimization that we use the classical LP and STP and those things. Tree packings loads an edge. As I said, I just review it with the number of trees. This is the number of trees. And a new concept which is called utilization of an edge is just the load of an edge divided by capacity. So utilization of an edge is load of an edge divided by capacity of that edge. So a tree packing, when I say a tree packing, it means T1 up to Tk is greedy if each of these Ti's is a minimal spanning tree with respect to the utilization that is induced by the preceding trees, because you can imagine that we have an order. So in enumeration of all minimal KV cuts, it means that after tree packing, first we do tree packing, and then we take each tree and consider all partitions that T crosses, but at most 2k minus 2 times. I should recall that spanning tree has less than n minus 1 edges. So from n minus 1 edges, you want to pick 2k minus 2 items. So